Okay, so what we're going to do now is to talk about the shape functions and make sure that we can really, from what we've learned in the 1D case, we can extend our knowledge and apply it to the 2D case. And we know exactly what to expect and what rationale to follow. So what I want you to do is to see if you can derive the shape function for N1. Okay. You're welcome to pause the video and give it a go, because you know what principle to apply. So the only thing that might be a little bit in the way is just getting around the algebra. But for the rest, everything is actually in place, because what we know is N1 is a function of sine eta. Make sure everything is recording, and that's what we have. What we also know is essentially this is psi. We know that this is eta. We know here at the top we have the line of eta equals to 1. This line here is the line of psi equals to 1. This line here is the line of psi equals to -1. This, the bottom here, is the line of eta equals to -1. And then, obviously, that's that. Okay. So that's essentially just to make sure that we're comfy, that we have at least those things there. So let's start off by applying our principle. Okay. So, again, the last chance to pause. Give it a go. Otherwise, let's continue. Okay. So the first thing I want to just mention is what we know is at N1, we want the shape function here to be equals to 1, and everywhere else it must at these other nodes it must be equal to 0. So let's knock out some of those nodes to be 0. And I need to just take at the roots and say, what are my roots? This is one root, psi equals to 1, so I can write it as 1 minus psi. That's my one root. Okay, and that will mean that if I have this true as part of a term in a multiplicative, if I'll multiply only terms together, because we're going to do a polynomial as a product of the roots, then what I know for a fact is that if I evaluate psi equals to 1 in here, at all of these nodes it will be equal to 0. Okay, what is another root that we have? Let's knock off the top one. So that will be 1 minus eta is the other root that I might have. There's one, the top one, 1 minus eta. Okay. And so essentially what I have is that these ones are also essentially 0. So the only ones are these two. I need to make sure that that N1, if I evaluate at these two spots, is also equal to 0. So what can I do? Well, the easiest thing to do is to say, well, what is the expression for this line? Can I write down some expression for this line and have that expression for this line as my root? I can. Because I had an expression for this line, eta equals to 1, or psi equals to 1. So what is the expression for this line? Well, it's a line that's at an angle, so we know for a fact it will be something that has both an eta in it, some expression. So let's write it such that if I'm on the line, it equals to 0. Okay, it's the same as what we did here. If I'm on the line, if eta psi is equals to 1, this expression is 0. And if I'm on this line at the top one here, if eta is equal to 1, then that expression is equal to 0. So let's write that expression that would make this equals to 0. Okay, so let's start off by saying I know for a fact what is the value here. So the coordinates here is essentially, let's just write down the coordinates for psi and eta. So the coordinate for psi and eta here is -1, 0. And the coordinate here is essentially 0 for psi and -1 for eta. That's what we have as the two coordinates. Okay, so I would like to have some stuff here that if I evaluate at this line, so let's see. If I evaluate now, if I'm at this node, yeah, I would like it to be equal to 0. So I want to say 1, and then I can say plus psi. If I say 1 plus psi, if I evaluate the coordinates in here, it will just be 1 minus 1. That's fantastic. And also I would like to make, so that's, I can see that 1 plus psi would work. Okay, I could even add in an eta, because the eta is equal to 0. But let's see at the bottom here what I want to do with eta. I want to make sure that if I add an eta here, that this still expresses to 0. So this 0, if I put the 0 into psi, that's 0, that's 1. And if I just say eta plus eta, then it will be just 1 minus 1, which is also 0. So I could really just say plus eta. And we can see it doesn't make a difference to these terms. So if I put in here -1, that's 1 minus 1 plus 0, which is just 0. And if I look at the bottom corner, I plug it in there, it's 1 plus 0 minus 1, which is also 0. So that works like a charm. So there's an expression for that line, 1 plus psi plus eta. Okay, beautiful. And that is essentially my expression for N1. now I need to make sure I scale this thing properly, because if I evaluate this thing, okay, so there's still a scale factor and stuff missing here. If I evaluate at -1 for psi, this thing must evaluate towards a 1. Okay, so let's put in here. If I put in a -1 for psi, this term evaluates to a 2. If I put in a term for -1 for eta, this term evaluates to a 2. Yeah, can you see? 1 minus 1 is 2. And if I put it in here at -1 and a -1 for tan eta, it's 1 minus 1, 0 minus 1 is what I'm left with. So that is essentially evaluates to a -1. So all I must say is, if I multiply this by 1/4, the negative of 1/4, there's my shape function. Yeah, for n1. Beautiful. That's just based on putting my roots down. Okay. And I can follow the same logic for n2 for the mid-side nodes and go around and really reason out what the shape function would look like. But this is just really applying what we've learned in the 1D case, writing down the roots. The only one that's a little bit different, maybe tricky, is the one that we just have to think about, maybe knocking off these two terms with a single line. That's that. But once we have that bit of insight, then writing down these shape functions become quite trivial. Great.